We will now begin our study of multivariate calculus. We start by studying partial derivatives. But first, we need to define what a multivariate function actually is. So we start with a function of two variables, which is simply a function of the form z equals f of xy that maps each ordered pair xy in a subset D of the real plane r squared to a unique real number z. The set D is called the domain of the function, and the range of f is the set of all real numbers z that has at least one ordered pair xy in D, such that f of xy is equal to z. So a multivariate function is much like the single variate functions that we were studying before, right? So we have our domain here, we have a set that we call the range here. What f does now, instead of just taking one point x, right, remember that was what single variate did, it took a point x and mapped it over to some point y. What a multivariate function does is it takes an ordered pair in the plane xy and maps it to some point z, which is a real number. So when we had single variate, right, this was our x value, let's say, and then the point f of x would be the y value. In multivariate, we now have three dimensions, right? So we take a point, let's say x, y, probably right here, right? Then f of xy is the z. So f of xy essentially measures the height the point is off of the xy plane, right? This is a height. And that's what z is measuring. So there's an image on the slide that describes this as well. So what it's doing, right, what the multivariate function does is it takes a point xy in a plane region, that's what this is called, and it maps it to a real number on a number line, so on an axis. So we're going to find the domain and range of the following functions. We're going to start with f of xy equals 3x plus 5y plus 2. Now, the same rules for finding domain that we had in pre-calculus single variate still holds for multivariate. Right? No zeros in the denominator. Right? And no negative under an even radical. As well as, of course, log x. X has to be greater than or equal to 0. So what you're taking the log of, I'm sorry, it's not equal to 0, right? It's just greater than 0. So what you're taking the log of has to be larger than 0. So we have no restrictions here, right? So there are no restrictions on the domain. So the domain would be the set of all points in the plane. Right? Another way of writing it would be the set of all xy such that x is a real number and y is a real number. Now, we need to determine range. So to determine the range, we set z equal to the function. Now, if y is 0, then we'd have z is equal to 3x plus 2, which would mean that x would equal z minus 2 all over 3. So this would mean that z minus 2 over 3 comma 0 is a solution to this function. And this is true for any value of x, or I'm sorry, for any value of z. So this would mean that our range is the set of all real numbers. Right? Or in interval notation, minus infinity to infinity. Now what about square root of 9 minus x squared minus y squared? Well, here we have 9 minus x squared minus y squared under this even radical. So 9 minus x squared minus squared has to be greater than or equal to 0. Notice that this means that x squared minus y squared is less than or equal to 9. So, I'm sorry, that should be a plus y squared, right? So the domain is the set of all ordered pairs xy such that x squared plus y squared is less than or equal to 9, where both x and y are real numbers. So again, to determine range, set z equal to f of xy. Right, so since we already know that x squared plus y squared must be less than or equal to 9, we get that 0 is less than or equal to x squared plus y squared, right, which is less than or equal to 9, because x squared plus y squared would always be positive, right? So this would mean that 0 is less than or equal to 9 minus x squared minus y squared, less than or equal to 9. So this value right here, let me use the color, right? So this value right here would be between 0 and 9. So if we have 9, right? So we're going to have 9 minus 9, that's 0. If we have 0, we'll have 9 minus 0, which is just 9. Square root of 9 is 3. So z can take on any value between 0 and 3. And so our range is the totally closed interval 0 to 3. Now, if we look at the domain real quick, x squared plus y squared less than or equal to 9. Well, x squared plus y squared equals 9, right, is a circle. It is a circle of radius 3. So if we're less than or equal to 9, well, equals 9 is every point on the circle. Less than or equal to would be every point, or less than would be the points inside the circle. So this domain is actually all of the points that lie on the circle of radius 3 or lie within the circle of radius 3. So the domain is a region, unlike in one dimension where the domain was a line or an interval. Now suppose that we wish to graph the function z equals f of xy. Well, this function, notice, has 2 independent variables and 1 dependent variable. So the graph would consist of ordered triples x, y, z, and the graph of a function is called a surface. All right, and I briefly touched on this on a previous slide. So imagine that the xy coordinate system is laying flat. Then every point in the domain of f has a unique z value associated with it. If z is positive, it lies above the xy plane. If z is negative, it's going to lie below the xy plane. And then the set of all the graph points becomes the three-dimensional surface that is the graph of the function f of xy. Now, graphing three-dimensional surfaces on a two-dimensional sheet of paper, or in my case, a two-dimensional tablet, is not possible. We can try to represent it three-dimensional, right? So, for example, we can try to draw a sphere and we represent it this way. By trying to imagine that this is three-dimensional, so trying to imagine that it's coming in and out of the screen, but it's still just two dimensions. So I will not be attempting any kind of sketching in three dimensions. If I put a graph up of a three-dimensional surface, it's going to be created using the program Mathematica. However, we can describe three-dimensional surfaces. One way to describe these is to use level curves. So imagine that you're a hiker and you're walking along a rugged trail. Well, you might have a topographical map that shows how steeply this trail is changing. Right? Well, this topographical map contains curved lines called contour lines. And each contour line corresponds to the points on the map that have equal elevation. Right? So this image shows Devil's Tower, along with the topographical map of it. So you can see we have all these level curves, right? Each curve, so this curve here represents 4,400. So all of these, so this line represents an elevation of 4,400. And as we're getting closer, right, we can see that it's getting higher and higher until this one right here represents an elevation of 5,000. Which means as we're moved out from the center, it's getting less elevation. The elevation is decreasing. And then here is a picture of Devil's Tower. Well, a level curve of a function of two variables is completely analogous to the contour lines on a topographical map. So given a function f of xy and a number c in the range of f, a level curve of f value c is defined to be the set of points satisfying the equation f of xy is equal to c. And the graph of these various level curves is called a contour map. So we're going to describe the level curves of this function. So remember to do that, we have to set f of xy equal to some value c in the range. So doing this would mean that the square root of 8 is 8x minus 4y minus 4x squared minus y squared is equal to c. Right? And this would mean that 8 plus 8x minus 4y minus 4x squared minus y squared is equal to c squared. Now this means, let's group things together. So I'm going to group things and also multiply by -1. So we're going to have a 4x squared minus 8x plus a y squared plus 4y minus 8 is equal to -c squared. So we can factor out that 4. So we have x squared minus 2x. We can't do anything with that second grouping. Is equal to 8 minus c squared. Completing the square. So we're going to have 4 times x squared minus 2x plus 1, then plus y squared plus 4y plus 4 is equal to 8 minus c squared, and then I have to add the plus 4 times 1 and the plus 4. So this is 16 minus c squared. Now this will give us 4 times the quantity x minus 1 squared plus the quantity of y plus 2 squared is equal to 16 minus c squared. And so we have 4 times the quantity of x minus 1 squared over 16 minus c squared plus the quantity of y plus 2 squared over 16 minus c squared is equal to 1. Now here, what we have to have is c being between 0 and 4. Right? Any other values would violate the range. So we now examine this function, this equation, at several values of c. First, if c is greater than or equal to 0, but less than 4, well then this would be ellipses, right? So the level curves are ellipses. Centered at, if we look, 1, -2. Right? The only thing that would change would be the semi-major and semi-minor axes, depending on the value of c we have. Now, if c is 4, then this is 0. Well, then there's only one solution. It would be a point, right? There's only one specific x value and one specific y value that would make this 0. And that's the point, -2. Right, and so this is a graph of the contour lines, right? This is our contour map. So there's a point, let's draw it, it's not shown, right at 1, -2, so it's probably, I don't know, right about there, right? So that corresponds to our c is equal to 0. And then, as c gets larger, you can see what's happening, right? So there's an ellipse, there's a larger ellipse, so on and so forth. And you can see that as c gets larger, these are starting to actually get closer and closer together. So this would be our contour map. Now, there's a second way of describing a graph, and that's to use vertical traces. So consider a function z equals f of xy. A vertical trace of the function can be either the set of points that solves the equation f of ay equals z for some given constant x equals a, or f of xb is equal to z for some given constant y equals b. So there are two vertical traces, right? There's the vertical trace for when x is equal to a. This is called the yz trace. And then there's a trace for when y is equal to t, and this is called the xz trace. So let's describe the vertical traces of the function sine of x times cosine of y. Alright, so if we look first at the yz trace, we set x equal to some constant a. Then z would equal sine of a times cosine of y. But this sine of a is some constant, right? Because a is a constant. Well then, these are just cosines, right? So the graph is just a cosine curve. Of magnitude, absolute value sine of a. Right, so since it's the yz trace, it'll probably look something like this. Something along those lines, right? So for the xz trace, we set y equal to b. Then we have z is equal to sine of x times cosine of b. But again, since b is a real number, this cosine of b is just a constant. And so the trace is a sine curve of magnitude, absolute value cosine of b. So since it's the xz trace, it would look something like this. Oops, I erased it. All right, it would do something like that. So all of these discussions, for the most part, can be extended if we have a function of more than two variables. Specifically for the domain. So find the domain of the following functions. The first one we're going to look at is 3x minus 4y plus z all over the square root of 9 minus x squared minus y squared minus z squared. Now, not only do we have a denominator, which means the denominator can't be 0, but we also have an even radical root. So this would mean that 9 minus x squared minus y squared minus z squared has to be strictly larger than 0, which would mean that x squared plus y squared plus z squared has to be strictly less than 9. So the domain is a set of all ordered triples x, y, z, such that x squared plus y squared plus z squared is less than 9, where x, y, and z are all real numbers. Notice that this is a sphere of radius 3, and it's all the points that lie inside the sphere, but not on the surface of the sphere, right? Because it's strictly less than. And let's look at the function square root of 2t minus 4 over x squared minus y squared. Right, well here in the numerator we have an even root, so we have to have 2t minus 4 being greater than or equal to 0. In the denominator, we have x squared minus y squared cannot be 0. So we have to have t being greater than or equal to a half, and we have to have x squared cannot be equal to y squared. So the domain would be the set of all x, y, t such that t is greater than or equal to a half, x squared cannot be equal to y squared, and then of course x, y, and t are all real numbers. So that concludes our introductory study of multivariate functions.